Hello everyone, I am Vidi, here to talk about Testing QUIC with packetdrill, and this is a joint work done with my colleagues Rui and Christoph at Apple. For quite some time, we have been working on IETF QUIC. There has been a lot of efforts involved in testing QUIC. When it comes to testing, I believe a lot of QUIC implementations already have unit testing. To test the interactions between different implementations, we participate in interop testing every other month, where we test our implementations on a set of core features. Additionally, as a part of interop, there is a throughput test to ensure that HTTP 3 is no worse than HTTP 2. As of now, multiple implementations are publicly available either in production or for experimentation, and many others are joining the club as we speak. With all these efforts to test our QUIC implementations, can we say that our implementations are ready? To understand a bit more about what kind of testing would help us to validate our implementations, we need to understand the key mechanisms of transport protocols, some of which are managing lifecycle of a connection, flow control strategies, loss recovery mechanisms, and congestion control algorithms. All of these mechanisms depend on a set of input and output sequences that occur at a specific time. In addition, we continue to add new mechanisms which complicate the interactions with the existing machinery even more. Testing QUIC has even higher complexity as QUIC adds a lot of new features, such as confidentiality and integrity protection, authenticated handshake, multi-streaming, large set of transport parameters and frame types, connection migration, and more. There are numerous pre-existing methodologies that can test transport protocols. Each of these focus on different aspects of the protocol testing and are able to discover different types of bugs. Some of the most commonly used methods include unit testing, interop and performance testing, protocol fuzzing, failure testing, longevity and stress testing, and conformance testing. Reproducible integration testing is a complementary approach which allows us to translate the bugs found by the above-mentioned strategies into a test script that can be run reliably in an automated manner. In addition, it allows the developer to create specific event sequences that can trigger certain behavior during development. Now, I would like to dive deeper into reproducible integration testing, which in simple terms is just black box testing with a set of inputs and expected results as output. I would like to demonstrate it with an example. Imagine you have a transport protocol stack that you want to test. To test the sending logic, let's say you call the send API at time t. At that moment, the transport protocol will create some state, initialize some queues, etc., will create a packet and send it out. Most transport protocols have retransmission logic to retransmit the packet when they don't receive an ACK within a certain period. Hence, the stack will retransmit the packet after waiting for some time, let's say X. Both these behaviors, that is, sending the packet and retransmitting it, can be verified by the test tool. The test tool then can choose to send an acknowledgement. packetdrill is exactly the tool that lets us perform this kind of precise, reproducible integration testing. The tool was developed by Google in 2013 and originally intended to be used for TCP. As a developer, you write a script where you specify what actions to perform at what time by calling the networking APIs, and packetdrill makes sure that those events happen at the exact specified time. The test script language supports 4 types of statements: system calls, packets, shell commands, and Python scripts. packetdrill allows a developer to verify both the correctness and timing of the expected response from the networking stack. The scripts run in real time on physical devices and can be very easily automated. In addition, due to its flexible grammar, one can easily add new protocol options. For example, TFO cookies in TCP options. For more details, I recommend reading the packetdrill paper. Now, I would like to give a high-level overview of how we test QUIC with packetdrill. To test QUIC, we first link the user space QUIC library into packetdrill. We also need to link a TLS library that would perform the authenticated handshake and generate keys. Let's say we want to test a QUIC client that is trying to connect to a QUIC server. At first, packetdrill parses the entire test script and creates packets corresponding to each packet event. When the script calls the QUIC connect function, packetdrill calls into the QUIC library APIs to start the connection. The QUIC library creates some internal state and begin the QUIC handshake by sending out the client initial packet to the local interface via UDP. This packet is sniffed by packetdrill, which then verifies the packet content and its timing. In response, packetdrill can choose to construct and inject the server initial, which is then received by the networking stack. To better understand the flow diagram, let's go over an example packetdrill script for QUIC. Every statement in the script has a prefix that represents the time at which the said event should occur. Note that the time is specified in seconds. First two lines are QUIC library API abstraction that allows one to create a QUIC connection and call connect-on-it respectively. Packetdrill executes the API calls and verifies that it returns the expected result. This starts the handshake where QUIC client library is expected to send out the client initial immediately after the QUIC connect. Note that the outgoing packet from the transport protocol stack is denoted by greater than sign. The DCID and SCID are internally mapped to actual connection IDs. Also note that the packet contains QUIC frames, which I will discuss later in the slides. Following it is the server initial reply constructed and injected by packetdrill into the stack. Note that we use a delay of 100 milliseconds before injecting this packet to simulate a RTT of 100 milliseconds at the client. The injected packet from the packetdrill is denoted by less than sign. After the server initial, packetdrill injects the server handshake packets, which contain the encrypted transport parameters, certificate, etc. The QUIC client library receives the server handshake and authenticates the server. It also sends out the encrypted handshake finished message. Once the handshake is completed, client can now send one RTT data. Now, I would like to go over the key contributions of this paper, that is, how we integrated QUIC into packetdrill. The first task was to create a packet grammar to represent and construct QUIC packets for all packet types and different frame encodings. Secondly, we added support for doing the authenticated handshake via a TLS library. As QUIC packets are encrypted and have their own packet and frame format, we added modules to decrypt, parse, and verify QUIC packets. And finally, we construct the encrypted response and inject it into the QUIC library. Defining a QUIC packet grammar is an important step to represent the various QUIC packet types and their respective frames. Here, I will show the general representation of the QUIC packet format. In the packetdrill script, a QUIC packet is denoted by a set of tokens. We start with the packet prefix, which contains the time and direction of the packet. Then we have the QUIC token to identify that it is a QUIC packet. It is then followed by the QUIC header and a list of frames. The QUIC header allows you to specify the QUIC packet type and other header fields such as connection IDs, packet number, etc. After the header, we have a list of QUIC frames. A QUIC frame is denoted by the frame type, for example crypto frame, and its associated fields. Let's take an example to understand the QUIC packet grammar. This is a client initial packet, and you start by specifying the time and direction of the packet followed by the QUIC token. Then comes the QUIC header, where you specify the values for packet type, DCID, SCID, and packet number. Then we have a crypto frame with values for its offset and length fields, and a padding frame with values for its length field. Similarly, we have the server initial packet containing the header and the list of frames. Note that we also allow to set server transport parameters within the crypto frame to exercise various protocol behaviors. Let's move on to the second item on the list, which is how we perform the QUIC cryptographic and transport handshake via a TLS library. As I mentioned earlier, we link the QUIC library that we want to test with packetdrill. We also link a TLS library to carry out the authenticated handshake. We added a packet protection module inside packetdrill that encrypts and decrypts packets by calling the crypto APIs. And we added a handshake module that exchanges the handshake messages with the TLS library. When we call QUIC Connect, the client library sends out the client initial to the local interface. It is then received by the packet protection module, which uses the initial key to decrypt it and passes the decrypted payload to the handshake module. The handshake module then sends the client hello to the TLS library. At this point, the TLS library generates the server hello and sends it back to the handshake module, which saves it in a buffer. As specified in the script, when it is time to send out the server initial, the saved buffer is copied into the outgoing crypto frame, encrypted, and sent to the QUIC library via the local interface. The TLS library also generates handshake and 1RTT secrets and passes them to the packet protection module, which then derives the respective keys from it. Now, let's take a look at how a QUIC library packet is parsed and verified by packetdrill. We have added a packet parser to parse the QUIC packet into its constituent header and frames, and a verifier to compare the QUIC library packet with the expected script packet. When QUIC library sends out a packet, it is first received by the packet protection module, which removes the header and the packet protection, and it passes the decrypted packet to the parser. The parser then parses the packet into the respective header fields such as DCID, SCID, packet number, and the list of frames with their respective frame fields. It then passes the parsed packet to the verifier, which performs a field-by-field match on all header and frame fields. The result is a pass when all the fields match. Otherwise, if any of the comparison fails, the test fails. And finally, we take a look at how we inject the script packet into the QUIC library. In addition to the already discussed elements, here we have a packet mapping module which maps the DCID based on the client initial and replaces the SCID specified in the script to a randomly generated 8-byte SCID. Also, for crypto frames, it fills out the crypto data that was received from the TLS library. Based on the test script, we wait for the specified amount of time before injecting a packet. When it is time, we send the script packet to the packet mapping module, which updates the DCID and SCID and send it to the packet protection module. The packet protection module encrypts the packet using the keys for the corresponding encryption level and send it to the QUIC library via the local interface. Now I will move on to the packetdrill test scripts for QUIC. Currently, we have over 50 scripts and we are adding more by the day. These scripts provide test coverage for most of the transport mechanisms, such as quick handshake, flow control, state machines for send and receive side of streams, loss recovery, congestion control, path MTU discovery, and more. We are adding new scripts that are continuously being integrated with the operating system, and the scripts are completely automated. We run these scripts during development, for regression testing, and to troubleshoot any issues found in the wild. As a part of this research, we also adopted a QUIC library other than our own and tested its QUIC conformance. This second library is Cloudflare's Quiche library. To adopt it, instead of linking our own library, we link the Quiche library into packetdrill. We created Quiche API wrappers for the test script to call into and added a thin abstraction layer to handle socket reads and writes and pass data to and from the Quiche library. We also needed a simple timer implementation to react to timer-based events. As we are testing Quiche, the test script calls Quiche Connect, which internally creates a UDP socket connection. It then calls into the Quiche library that creates the client initial packet, which is copied to a buffer. The send abstraction invokes send system call with this buffer on the UDP socket. The rest of the flow is similar to that of our implementation. With the help of its easy-to-understand documentation and examples, it was quite straightforward to integrate Quiche into packetdrill. We added just a few wrappers and a simple timer, which was less than 300 lines of code. Regarding the test scripts, we reused the same scripts with a minor change in the API names. For example, Quick Connect became Quiche Connect, and there were very few changes related to the size of certain packets. While testing, we found some issues in Quiche library with respect to the contents of PTO retransmissions and certain protocol error behaviors. Since then, we have worked with Cloudflare engineers to resolve these issues. As QUIC provides a lot of new features, we encountered some new set of challenges during this work. Firstly, we noticed that certain mechanisms during handshake, such as cert validation or key generation, may take different amount of time on different devices. This introduces a bit of variability, causing the scripts to fail. We solved this problem by using tolerance and time intervals feature of packetdrill. Secondly, a QUIC script must start with a handshake just like a TCP script. However, a TCP handshake can be expressed in 3 lines, whereas a QUIC handshake is usually around 40 lines in the script. Rewriting this for every script is quite tedious and can create inconsistencies or typing errors. To solve this issue, we created an include-like functionality for our QUIC scripts, where 2 lines inside a script expand to a full-blown QUIC handshake. Finally, as QUIC is still an evolving draft, it requires us to update packetdrill on a regular basis to the newest draft. As we support multiple draft versions in our QUIC library inside packetdrill, we simply call the QUIC library's Connect API with a specific ALPN. This automatically sets the client version and no change is required in packetdrill. In conclusion, I would like to emphasize that packetdrill is a very useful tool to carry out controlled testing, and it provides the ability to explore the various protocol state machines. In this work, we show that after integrating QUIC into packetdrill, we can easily reuse code and scripts for validating any QUIC library. Testing QUIC with packetdrill proved very useful in finding numerous bugs and improving the overall quality of our implementation. We think that this approach of conformance testing can be very beneficial to the broader community and help create higher quality QUIC implementations. With that, I would like to thank you for your attention, and I would be happy to take questions.